Hey everybody, Jeremy here. Welcome back to the Towards Data Science podcast. Today's conversation is going to be really wide-ranging because I'm talking to Stanford professor and co-director of Women in Data Science, Margot Gerritsen. Now, Margot has done a whole bunch of working and thinking around AI ethics as well as where the rubber meets the road for AI applications in the real world. That's what we're going to be focusing our conversation on about today, but we'll also be discussing another really interesting topic that has to do more with the philosophy of AI, and that's this distinction between the way AIs learn about concepts and the way that humans learn about concepts through things like physics. Beyond that, we'll also be talking about the importance of soliciting input from people with diverse points of view when developing AI algorithms that are going to be used and consumed by people all over the world. And we'll be discussing more broadly the issue of the ethical development of AI technologies at top firms like Google, Facebook, and so on. So I'll leave things here because there's a lot for us to get to. I hope you enjoy the podcast.
Hi, Margot. Thanks so much for joining me for the podcast.
Yeah, terrific. Thank you.
You've done a lot of thinking about the unintended consequences of applying AI to solve certain real-world problems. In that vein, one place I wanted to start was just by asking, what do you think are the biggest problems with the way that AI is being used and deployed today?
Whoa.
It's a nice big question. But
it's a lovely, huge, absolutely huge question, and a question that we think about often, we being, academe, but of course also increasingly in industry and not-for-profits. There's a couple of fantastic not-for-profits that do that and advocates. For me, I'm going to give you an answer that comes from my background as a mathematician or computational mathematician. And so it's maybe a bit of a funny answer to some of the people in your audience. But I think one of the biggest problems with AI as we see it now, and let me define this a little bit more, because AI is a very fluid concept, of course. So when I talk about AI, I typically talk about these very large, deep neural networks, the deep learning that people are applying now to solve, very complex problems. And I think the biggest problem for me is that we don't quite understand how they work. Well, we know how we coded them up, and we know what sort of computational algorithms we're using, but we don't quite understand why it comes up with the answers that it comes up with. In other words, you cannot really interrogate these systems very well. This is the reason why we now have this, and I'm very happy that we do, but this new, very trendy area called explainable AI. And in a way, that name already tells you we had a problem, right? Because what other field do you know where you have the main field, like AI, say fluid dynamics, and then you have explainable AI of explainable fluid dynamics? Well, I've never seen explainable linear algebra or explainable optimization or explainable business decision making, but we do have explainable AI, and the reason for it is that there is this lack of interrogation. And so if you cannot interrogate a system and ask, why did you come up with that answer? Because it's just way too complex and convoluted, the way that these decisions are made by these algorithms. You can also not find out whether or not the answer is right. So you cannot really understand whether or not it is wrong. And this is the big problem, right? So when I give talks on AI, and people ask, why is there such hoopla about bias in AI or ethics? Why can you just look at the system and say, this is not biased or this one is biased, and this is the reason?
Yeah, I find it really interesting as almost a step back, the comparison to other fields, and saying we don't have explainable fluid dynamics, we don't have explainable economics. And it's sort of interesting. It makes me wonder, what is the fundamental property of AI that makes the decoupling between the explanation and the result possible? What is it about this space that kind of creates that natural separation?
When you look at these deep neural networks that people are using, you could map those onto a system that in the limit becomes a system that we're very familiar with. And so here is an area of explainable AI that says, look, if you build these deep neural networks, which are really nothing but a whole bunch of nodes, many, many millions and millions and millions of nodes that transform and transfer data from the input to the outcomes. And at every stage in this process, you manipulate data a little bit. You bring them together, you transform them with some sort of function or combination of the values, and you pass them on to the next node that again plays with the data, and so on. What you could do is to say, hey, what is actually happening through this process? And if we looked at the limit of this, so lots and lots and lots of these little manipulations, then we can start modeling this as what we call a continuous equation. And so that is either, for those of you who do mathematics, a system of ordinary differential equations or a system of partial differential equations. So in other words, what you could try to do is to say, hey, all these millions and millions and millions of relatively simple manipulations of data that you're doing, you can actually see this in a model. You can see that as representing this this more general model that you then can interrogate. Because if you had a system of partial differential equations that in essence represents what's happening in this deep neural network, then you can interrogate that system with the tools that we already have, right? So systems of differential equations are very relatively well understood. And so that's interesting. So you take a system that really came out of sort of a trial and error system. It really is about calibration. People always talk about you have to train with data. So you're really trying to calibrate all these manipulations that happen in the black box so that you can get from the input to the desired output for the training images. And that you can then say, hey, all that stuff that's happening sort of on its own, during this calibration and training process, we can now map onto something that we can understand. So that's intriguing, and there's several students that, for example, that I know in the Institute of Computational Mathematical Engineering on campus that I used to direct that are working on this, and they've really managed to take that further, and fantastic colleagues of mine like Lexing Ying and others who've really been looking at this.
So that's fascinating because it challenges, I think, one of the assumptions that I was making about the reason. Like, if I had to guess initially, I would have said, it's because we're kind of outsourcing our own computations to AI systems. When we train an AI system, we're sort of asking it to do all the thinking for us. Whereas in the context of physics or economics, like, we're doing all the thinking, we're infusing meaning into all the variables that we use. We sort of like have this a priori, let's say, preferred basis, preferred perspective on what variables are relevant and important to look at.
Yeah, no, I think that was such a good point that you were making. And so I come from an area originally of math, computational mathematics, that was really fluid dynamics. I did quite a bit of that for a long time. And how do you set up a simulation of fluid dynamics? A model, like a virtual laboratory that you use to understand things better, right? So you use to improve understanding of fluid flow. We actually build sort of virtual laboratories. And so you could think about that also as a black box, right? So and then put that next to sort of this black box of AI. But what's the difference? Well, the black box for this fluid dynamics, we start this from physical laws. So we say, hey, we actually understand not what this particular system that we're interested in is really going to do. That's why we want to build the virtual laboratory so we can observe, right? Mm-hmm. So we can learn. So maybe we're building it for a situation where there is a new object in the flow that may do something funny, like a new airplane or a new car, right? And we want to understand what is the drag on that car. Or we're looking at an area of the ocean that we've never explored, and it's kind of funny looking. There's some deep sea canyons, and we have no idea what they will do to particular fluid flow. So we do not understand that particular system. What we do understand is what rules that system. So we understand that if you're building a fluid flow simulator, that ultimately, no matter what is in there in terms of topography or objects, everything will always be ruled by fundamental laws. So you have a conservation of mass, you can have conservation of momentum, conservation of energy. And so you can build physical, you have these physical laws, and you can build, and people have done this over centuries, mathematical equations that represent these laws. And then you've got conditions surrounding those equations. We call them boundary conditions or initial conditions, and say, hey, you know what? Here are the laws that are governing a fluid flow, and the fluid flow is embedded in this particular system. Here are the objects that are in that flow. Here is the shape of the domain that we're investigating. And then together, you rock and roll, right? So you can now let this...
Make predictions.
Yeah, you can let this black box go. But we know fundamentally, we understand what we're prescribing in this. And those are these laws. Now think about... And sorry, so let me go back to that a little bit. Of course, data comes into that too, right? Because we need to know, well, what kind of fluid is it, and what is the density of that fluid? So there's a data point. What is the viscosity of that fluid? There's a data point. You know, where are these objects located, and what sort of surface area do they have, and what sort of friction coefficients, and so on. So there's a lot of data that goes in, but it's the laws and these equations that we're solving, representing those laws, that give us the final solution. Now go to an AI system. So I call this system, that first system, I called it data supported. So we need data to drive it. But now we're going to a situation where we don't look at the laws, right? So we just say, let's think about this ocean situation. Say we want to understand the flow in this ocean. And now somebody comes in and said, you know what? We're just going to observe this. We're going to send all sorts of little submarines in there. We have buoys. We use remote sensing from satellite data. We just got a whole bunch of data of the last couple of months of fluid flow in that area from what we can see. Now, you can never see everything, right? But we get a whole bunch of data. And then we play little games like, hey, 2 months ago, it looked like this. And 1 month later, it looked like this. So what happened in that month? What was the fluid doing in that month? So that's the question. In the simulator, the virtual laboratory that we built, we give the situation 2 months ago of initial conditions and then say, you laws and governing equations, go do your thing, obeying those laws, you know, with all this mathematics, and tell us what happens a month later. On the data side, we say, no, we don't know anything about the laws, but we have a lot of data of what we've been seeing. So let's see what sort of relations between the data we may be able to find that goes from the situation 2 months ago to the known situation 1 month ago. And we do that through this neural network. So we say, hey, we have a situation here. We have a month later, we have an outcome. And we want to find functions or relations that take us from the input data to the output data without the laws. And we do this with all sorts of different manipulations. We're guessing, so we're putting a particular type of manipulation on it that's not driven by the law, but it's just something that we understand a little bit mathematically. And we try. So we see how well that does, and it doesn't do so well. And then we go back and say, oh, where may we manipulate what we're doing to get an answer that's a bit more closer to the outcome. So, but you're purely looking at data. There's nothing really physical in this right now. And you keep doing that, and you keep trying to perturb that system of these data manipulations until you're nudging it closer and closer to this final outcome. So this is pure data manipulation. And the more data you have, the better that probably is going to be. But if you're missing some data, right, and if suppose that with physics we see, hey, you know, if you run this for several months, then at some point a certain phenomenon will start to develop, but you have to run this for several months. Well, if you have observation data only for 1 month, you may totally miss that, right? Yeah. So there is, you're missing information. So that's how you could see this difference. In an explainable world, you say, hey, I understand the rules governing this system really well, they come from physics. They come from, say, rules of human behavior. Yeah, you could even argue that some of the stock market analysis that people have been doing is controlled by rules that we have observed, we've derived, we've modeled for a long, long time. Whereas in AI systems, in these non-explainable AI systems, you don't. You really just manipulate over and over with trial and error and see what sort of manipulations may nudge me closer to this answer. And then you do this for a whole bunch of different training images, and then you say to yourself, hey, if I can do this, take initial data and get the outcome that I have observed several times, then maybe now if I start with new data for which I've not observed the outcome a month later, say for the ocean, maybe I can now trust it. Mm-hmm. Because somehow implicitly in all these little data manipulations that I've done, there is some truth. Somehow these manipulations represent these rules that I have on the physics-driven side.
Yeah. Oh, well, sorry, I was just going to add, it seems on the explainability side then, this is really interesting that you bring up this idea of like physics versus like what's going on in a deep neural network, for example. It's almost as if the key, or it sounds like one of the keys, is that in the case of the physics or the economics or whatever field, what's happening is we're choosing abstractions that map onto entities that we implicitly understand. So we talk about, in physics, we talk about masses, and we talk about energies, and we talk about friction and things like that we feel like we have a handle on. Essentially, we force the problem to express itself in a vocabulary we can understand. Whereas in the case of the deep neural network, we're basically facing a completely unconstrained problem. We're saying, look, solve this problem any way that you can. And presumably, I mean, that seems like a higher variance outcome, because in some cases, you'll get a solution that you never would have thought of if you were constrained by natural human understandable language. So you might get something better. But on the flip side, as you say, like at that point, you're really kind of putting all your faith in the data that you have. And if that data leads you to incorrect conclusions, you have no way of really peering inside and saying, hey, that's an error.
Yeah, and this is what you often hear people say, right? Is, I mean, the beauty of these AI systems that sometimes you get these unexpected outcomes that may actually shed a different light on something. And that may be true in certain applications, but of course, in the physics case, we want those constraints because we know those are true constraints, right? And so if we get something outside of these constraints, something unexpected, that may actually be violating these laws that we know should really be met. Okay, so there's some interesting things here. And yes, people are trying now to use AI for these physical systems as well. And then, of course, you try to impose some of those rules that we have explicitly imposed really directly because they're driving the modeling of the system from first principles on this physics simulation side. Of course, you try to impose some of these rules also, maybe indirectly, on what this AI algorithm is doing. And that's a wonderful area of research where people try to say, hey, how can we constrain all these manipulations that we don't really have a direct handle on inside the AI system? How can we constrain that a little bit more so that we direct it along, so that it obeys these constraints that we know really should be on it. Mm-hmm. Now, there are other systems where we don't have this, where we actually don't have existing models, and we're then can be very surprised at the outcomes of the AI algorithm. The problem, of course, is that when something unexpected comes out, if you say, well, the black box gave me that answer, so it must be right. It's unexpected, but it must be right. Mm-hmm. Or it may seem a little biased, or it may seem a little bit, not contrary to what we were thinking, but it must be right because it comes out of the computer system. You could be in a whole heap of trouble. And this is one of the things that is happening, I think, is that a lot of people that are using these AI algorithms, they don't really know how fidgety they may be, how not robust they could be, for example. And they just see it as a black box, and they have faith in it. They sort of start to believe in it. and they say, okay, we use this black box and it must be good because it's super sophisticated software and this has been developed by the best of the best, and Google uses it, and so if I use that box, then I'm gonna run with the results that I get. And so very often you see when new tools are developed like this, and people get very excited about it, and it requires relatively little a priori knowledge, because all you need is a whole bunch of data, and then the algorithm sorts itself out. In fact, we have companies, consulting company on this, saying, just give us your data. You don't need to give us your domain experts. You don't need to tell us much about your application. All we need is your data, and we'll tell you what's going on, because we have these universal tools that we can apply to all data. Now you are in a really dodgy area, right, where you have to be super careful.
Yeah, and from an ethical standpoint, it's funny, the language you're using, as you were saying, basically rely on Google, the best people in the world, or whomever, to come up with an algorithm that makes sense. It's a sort of language of unloading our anxieties and our ethical responsibilities onto something that's like away from us, so we don't have to take the blame if something goes wrong. It kind of feels good and comfortable to say it's handled.
Yeah, and this is exactly what you see now, right? When people say things like, hey, AI has an ethics problem and there is bias in it, a lot of people say, oh, it's not AI. It's not the algorithm. We're just manipulating data. How can that possibly be biased? If you have bias, it's just the data. So your data are not good enough, right? And so a lot of people say, we don't have a problem. If your data is good enough, and then of course we have to think, well, what does it mean to be good enough? Then AI is fine. There's no bias in that program, and I disagree with that. I do think there is bias, and this is because these programs never are written from a clean piece of paper, right? You never say, okay, I'm going to write this pure program. Right? These programs always are developed through lots of iterations with a lot of little manipulations and adjustments and tweaks and so on. So you start with a really good concept of how you may do that data manipulation, right? So I talked about these layers and layers of these data manipulations. And so you come up with, what sort of manipulations may be useful for us here? What sort of functions are we going to use? What sort of transformations are we going to use? What sort of combinations of data are we going to use? How we're going to design our layers of this propagation of data from input to output. And then you say, okay, now we're great, right? So no, you write a code like this, you have ideas, you think this may work really well, and then you go try it out. And you try it out on data, and that data may very well be biased data, incomplete data, self-selected, narrow. There's maybe, a bias in the sense that you're only looking at a subset of problems. Say you're doing human behavior analysis. Maybe your data mostly has information about white people. And so you start training and tweaking your algorithm, and that algorithm changes. And so it's never the pure algorithm and the data. It's always an algorithm that it was designed and then tweaked and improved, really based on testing, based on experience. And so there are lots and lots of opportunities for bias there to creep in. So as a designer, you may say, oh, this particular manipulation seems to work better than others. But mind you, it seems to work better than others based on the data that you've been looking at. Not necessarily the data that you're going to feed it in later to solve the problem that you're interested in, but the data that you're using to convince yourself that you're onto something good. And so then as a programmer, you select. You say, okay, this works better than other. Maybe we should do it this way, maybe we should do it that way. Or you're taking a fantastic result that has been advertised at a conference from somebody, say, wow, they get really great result with this. Let me just take that and use that, without really knowing what they ultimately tweaked it on or trained it on. So you have propagation of bias in what you put in the system, on how you've trained it also, right? And when you use open source software, for example, to build your complex products, you usually use bits and pieces of code that others have done. You look at the highly cited papers to say, hey, this is the latest and greatest, maybe we should use that. So there's a lot of that propagation of, actually of things you don't really understand, what people are doing.
Yeah.
And then there is this desire, sorry, I'm on the soapbox now, but then there is this desire, Jeremie, to of course publish ASAP, right? So this you should never forget that areas like this, these are hot areas, people make their careers on this. People want to be the first to use a particular algorithm for a new type of applications and put their stamp on things. I want to be the first to use AI for ocean modeling. I want to be the first to use AI for this decision-making process in this industry where it's never been used before. Because if as company I do this, it becomes PR. I can sell myself. I can say, we are doing AI. We must be so much better than the others. So there is this incredible rush to sell fast, and maybe without, really interrogating that black box enough, right? So I see things being put out. And then if I ask as reviewer, for example, hey, have you tried to see what happens if you perturb the data a little bit? What if you, if you try this on yet another set, what if you make these layers a little bit different? Would you still get the same outcome? You're sort of saying, hey, what if I take that really complex system and I make a perturbation that I could have made? It's just sort of a random thing that I got to where I am. So if I sort of randomly perturb it, I want robustness. I want the same outcome to be there. Do you actually see that? A lot of the times they say, oh, we didn't have time for this. Because running this deep learning algorithm takes a lot of compute time. So they only do that once, or they do this a couple of times. So anyway, there's a whole bunch of stuff going on here.
I love I love the issue you've just raised. It resonates deeply with me because I did a grad school in physics. I was a researcher in physics for a while, and we had the opposite problem. So we had this interesting situation where the laws of physics are kind of known. Like there's no mystery. Like you were saying, we have a really good sense of like how systems should behave. And I was doing experimental physics. I set up a whole bunch of mirrors and lenses and lasers and stuff and whatever. Anyway, we're supposed to get some outcome. And we knew what we were supposed to get. There was never a question. We were just trying to manifest an effect that we knew should exist in nature. And that meant that if we set up our experiment and we didn't get the effect that we knew we should see, we'd say, oh, we did something wrong with the experiment. Let's try again. And we would keep iterating, right? And like, there's a sense in which that's kind of not really like real science in a sense, because you're sort of like, you're cherry picking in a way, going through like tweaking the experimental setup. Do we get the result we know is true? No. Okay, let's try again. You'll only ever succeed at confirming stuff you already believe if that's the approach you take. Whereas what you're highlighting here, which is fascinating, so the other side of that academic coin when it comes to data science is like, well, if my algorithm can be tweaked with just like a little change here and a little change there, and the output deviates completely, then I can make any output happen that I want just by tweaking the system. And like that seems like a really serious problem, right?
Yeah, well, so it's such an interesting thing to juxtapose these two approaches, because you're saying if we don't get what we know we should get, we make a mistake. And in fact, this is what I tell my students all the time. If we think about physical simulation and the outcome looks weird, I tell them you've got a bug in your code, figure it out. This is not what I think or I know should be there. So, and in AI, yes, we don't do that as much, but I do think a lot of people want to get the outcome or trust the AI when they get the outcome they think should be there. So they may not know it, like in your physical experiments, but they have a preconceived idea of what it probably should be. And this is, and then it's very likely with a system that it has so many places to tweak, so many places to tweak the system, that you could actually tweak your black box until you actually see what you think you should be expecting. Now, is the physical world that we're describing of research much different? No, right? I mean, we're also setting up an experiment, but ultimately, of course, this experiment, it's actually the molecules and the rays and the photons or whatever we're looking at that are actually showing us that behavior, right? We're not making up new particles. We're working with real things. We're working with fluids. We're working with with thermodynamics and this just the natural world that we're applying. So in AI, yes, it is that concerns me that if you have a preconceived notion of what you think will come out, you can always convince yourself then if you manipulate this enough that indeed that is what you need to get. And that or here's another thing that can happen, which is a really interesting difference, I think, between what we used to call the scientific method and what we're doing now. See, in the scientific method, the way you were raised and I was raised, in physics, is what is the scientific method? You say, okay, I want to understand something. I have prior knowledge, about this. Those are the physical laws, for example. Mm-hmm. I'm going to set up an experiment so I can get the data to see if I can prove a hypothesis that I have or more disprove, right? The hypothesis. That's the scientific method. So I've got some prior information. This is all this knowledge that we have out there about the physics. I have a hypothesis about a new phenomena that people haven't really looked at so well. And I'm now going to collect the data to see if that hypothesis can be passed or not. So that is what the scientific method is. So you collect data afterwards, but you don't start with the data. So now we have a situation where what we start with is not this prior knowledge in terms of the laws, on the shoulders of, centuries of great minds. But what we start with is data. And of course, when you have data, the first thing you're going to do before you actually build models is to just sort of see what's in that, right? Mm-hmm. So that's logical. So the first thing you do when you have a whole bunch of data, you start data mining that a little bit. Say, hey, what do I see? What sort of patterns do I see? So suppose you want to understand the system and you have all this data already. Then the first thing you're going to do is say, hey, what do I see? Then, of course, you start building ideas about what this system actually may be what actually may be driving that system, right? So that's actually what you want to find out, but you're looking at the data and you already get some ideas because you may see some patterns, you get a feel for the data. And then you start building your AI code using that same data. So now you've gained a little bit of a feel for the data and you're using the same data to then see whether or not your algorithm may get you what seems to be the truth. So that's not quite the scientific method anymore, right? When the data comes first, and then you're using that same data later, it's really hard to say, hey, wait a second, I'm actually, in Bayesian statistics, you have this idea of a prior, which is sort of all the knowledge that you have on which you base this sort of hypothesis, and we sort of see this prior as, hey, this is validated, data, and now you're sort of replacing that with preconceived notions that come from interrogating the data that you already have in advance. Mm-hmm. And so in a way that makes you wonder if that sort of Bayesian statistics on which we actually which is actually the foundation of many of these machine learning and AI algorithms, if that's really still applicable, right? And it seems we're getting away a little bit from this scientific method in that sense.
Yeah, it's actually, so this is, the analogy you're drawing between these two, I'm finding it just keeps going deeper and deeper. There's one, actually one thing that pops out at me, like, it feels like it's not the scientific method on the AI side. In some sense, it's almost as if it's kind of like what we were doing with the scientific method before we had scientific knowledge. So in other words, if I imagine a human being in a cave, not that, I don't know if we were actually cave people at some point, but whatever. If I imagine, that's where we began, with no knowledge about, F equals ma, Newton's laws, or anything like that. I'm just sitting in a cave. And I start to look at the world. Functionally, what I'm doing is a lot like what that neural network is doing. I'm just taking in data and I'm trying to map that onto, like, I'm trying to build some sort of decision apparatus between my ears and my brain to kind of start to make predictions. Over time, I get a more and more firm sense of what some of my priors should be. And then I pass them on culturally, and hopefully they infuse society and get enshrined, and we get physics. But it's almost as if physics is like the product of a lot of these chained neural networks in a way.
I love your analogy. A lot of people say, hey, but the difference between the caveman trying to, from the data that he's observing, so saying, hey, if I see this, then a week later I see this, or I see this an hour later I see this. Mm-hmm. How is that connected? How do I go from one end to the other, the way we've been describing? We can accelerate this now, people say, because we have so much more data. Mm-hmm. So we're so much better off than this caveman. It's like having, 100 billion of them together that are all sharing what they have observed.
Yeah.
And then you say, okay, we have this collective intelligence that we're not over years and years and years and years and centuries and millennia translated into these physical laws, the way we understand it now, this mathematics, this language that we designed to capture that, mm-hmm. and to say, okay, this is the essential part of this, of all these observations. Instead, you're sort of saying, no, we have all this unbelievable amount of data, and that process can be accelerated, so we don't need this millennia, yeah. We don't need to go through all these people thinking about it, and then at some point understanding sort of first principles of this, and then modeling it, and then taking it further. We can just stay with the data, because if we have 100 billion observations and thought processes of a human intellect, and we can combine all of this, we get to the answer much faster just based on that data. And that's exactly it, right? So you're trying to accelerate human intelligence by combining, if you like, this power of the many, 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 many observations and deductions that humans otherwise would make and maybe translate into laws. So I love that you're saying that, because that's exactly what they're trying to do, and what we are doing in a way. The thing that makes me uncomfortable, and some of my colleagues say, well, you're more old-fashioned maybe in this, is I really like getting to this foundational understanding. When I look at fluid flow, yes, as a kid and as a student, I observed a lot. I was looking at the cloud saying, why is this cloud doing this? Or why does it have this shape? And I was trying to predict, what is it going to look like an hour from now? As I was lying in the grass looking up at the clouds, or wind patterns or flow patterns. I was fascinated by this. And I was always asking, why is it doing this? And what I wanted to know is, what is really driving the physics, right? Well, what are the rules that the physics is obeying? And I think that question has driven so much research. And people really wanted to know the why, but why, right? And my son used to say this all the time when he was little too, right? Is the why. And here with this other approach, you say, you know what? We're not really looking at the why. We're just looking at the what. Mm-hmm. So we're saying, what will be the result later on? Not what are these fundamental sort of processes of these molecules or these, these other physical things that make this happen. And Einstein, of course, wanted to really understand this too outside of our own world, and Newton wanted to understand it in our world, and all these greats that we're looking at this side. And now we're saying, we're not so interested in the why, we're just interested in what.
What's the prediction going to be?
What is it going to be, right? And so there's and we think, or the community thinks, that if we just have enough data and we can mimic that process that you were describing, but very, very fast, we can also get there.
Yeah. Well, so, and I feel like I feel like it's exactly that speed. Like, one of the constraints the unspoken constraints that's imposed by this very slow process you're describing over generational time, millennia, surpassing knowledge from one generation to the next, is people in that process to pass along knowledge are forced to articulate knowledge in human understandable terms. And so with every generation, the only knowledge, the only memes, the only ideas that propagate are the ones that can be expressed using symbols and abstractions that are comprehensible to the median human being. Things like mass and energy and gods and stuff like that, all the stuff that we resonate to. Whereas like this AI system does not have that constraint. And so when we ask the question why, or when I ask the question why, I feel like what I'm begging for is an answer that uses human understandable abstractions. I want an answer that uses words like apple and words like energy and words like force. I don't want an answer that's like, well, here's the matrix mathematics that gets you to that. Like, I could look at the matrices, I could look at that, but it's like the language is wrong. It somehow doesn't tell me, like you were saying, that fundamental truth that you're so hungry for.
I'm with you on this. And so one option I do really see, which we talked about in the beginning, is this math. If you can map it onto the mathematical language that we have. And what is mathematics? It's really just the language to communicate the why and these sort of relations, right? And causality and between behaviors, between observations. We use mathematical language to communicate that. So, I can try to describe it in words, or I can try to describe it in this mathematical language. That was math was invented for. And so if we can map what's happening in these deep neural networks to more of that mathematical language that we understand without it being so obfuscated, without saying, yeah, there's math in there. All these manipulations are mathy. Absolutely. Mm-hmm. There's no magic in there. It's all, if you look at what happens at every moment in time in these calculations, totally understandable. Maybe they do some sort of transform. Maybe they combine, they add some numbers up. We understand that. What happens at the elementary level perfectly well. There's no magic. And some people do think that there is this sort of magic dust in these AI algorithms where they do things that are totally unexpected. No, everything that this computer does is what we tell it to do, or at least play with, right? Mm-hmm. It's the combination of everything that they do that may lead to something unexpected. But if we can make that at a higher level, so that it is the behavior that the overall behavior at a higher level that we can understand in that language, that would be so great. And I think we're going to be seeing a lot more of that, right? A lot more of that. And the other thing that in this wonderful analogy between a long, slow process over many, many years versus this really quick, hey, we have this unbelievable amount of data now, let's do it all in one go approach, is that over this long, slow process, you do have this interrogation of, can this be true? You do have this, is this robust? Maybe this is wrong. And of course, in the history of math and in the history of physics, there have been many, many things that people thought were right and later proved wrong. And often that came with more observations, with better thinking, with understanding this math maybe a little bit more, by other people scrutinizing the mathematics, say, hey, you do mathematical manipulations, you can't do this, you can't, that's wrong. And so we have these checks and balances in place and this scrutiny that comes through, and you need time for that. Mm-hmm. Now, here on the AI side, everything is going so fast that scrutiny is actually coming after the fact, right? Mm-hmm. So I sort of see as the community is jumped on it, pushed it, saying, wow, there's such really interesting things that we can do with this. This is all very fascinating. And now saying, oh, but wait a second, let's go back and really interrogate this now and understand that better. So it's a totally different process. We're here, the checks and balances were they're on the way in progress. And here we went full force and said, oh, hang on. And I think a lot of people are getting burned now because of this, because of very fast adaptation. Sometimes I advise companies on this. They ask, hey, Margot, should I, my competitors are using AI for this. What is in this for me? What can I do with this AI? Is it all a big hype, or could this be competitively advantageous? And so there's PR there and there's actual outcomes. And when you look at actual outcomes, a lot of these companies are not really getting much bang for the buck, apart from the PR side where they can say, hey, we're so sophisticated. And the reason is that it's too fast and too furious, and we don't really understand it, and there's a lot of bugs and there's a lot of errors, and a lot of the time then you come to a screeching halt and you have to say, oh, wait a second, let's now try to understand. So that's what's happening now, say, oh, why is this actually happening? Why are we actually getting these results?
Yeah.
How can we maybe interrogate the system to see if there's bias inherent in the system? All of that is now this wonderful area called explainable AI. And I think it will slow down. It will be a while before we really understand. And my own thought is, but maybe that's because, I've got a narrow brain, can only do so much, is that ultimately we'll make progress in there if we can map what's happening, complex data manipulation system, to the math we already understand. These differential equations, for example, that I talked about earlier.
And where I guess the symbols actually mean something like human understandable in those differential equations.
Where they're not ambiguous, right?
Yeah.
Using if you can say, hey, this is just like this particular mathematical statement. There's no ambiguity there.
So, and you referenced something really interesting when you start talking about companies that come to you and say, hey, my competitors are using this AI system, like, should I build one? How can I build one fast? And this is something that, I'm personally pretty concerned about the prospect of a race to the bottom on safety, on alignment, on ethics. The idea that one company looks at another company and says, well, they're focusing all their time and attention on making the most powerful systems that they can, the biggest neural networks, the most horsepower, and so on. And they're investing next to none of their time into safety or security or ethics or what have you. So I can't afford to do the same at my end. We all have to compete on this basis where, again, kind of economically speaking, like a race to the bottom. Like we're all going to invest minimally in safety so we can beat each other in capabilities. Is that something, first off, would you agree with that characterization? I would imagine you have some experience with the industry side. And second, do you have any thoughts, if you do agree, about how to resolve that or how it might get resolved?
So I'm not sure if we're going to get this race necessarily to the bottom, but the whole thing really is happening to some extent because of the hype around this, right? Why are companies doing this is because their potential customers actually believe the hype of AI, believe that unless now you're using AI, you don't really know what you're doing, right? So there is this, and I'm exaggerating here, but there is a bit of discounting of the old domain expert going on. Why would we need an engineer? We just need a data scientist, and this person can also help us with this. So people have been discounting this domain expertise to some extent. Now, I don't believe in that. I think you need that domain expertise. But if you believe in that hype and you see, and the customers believe in that, then you can get into this vicious circle where the customers believe it, so they go to the people that have it, and then other people say, well, we also need to have this, but ultimately, an industry can only thrive and survive for so long based on hype. But ultimately, a customer will realize, hey, the additional benefit I get from this company is not much different, than what I got from others. A customer may start to realize, this is great, and I can now claim to my customers, hey, I'm using this intelligent thing, right? So they sell this on. But at some point, it's the results that are most important. And they may start to ask, why am I getting these outcomes? They may start to say, hey, this was unexpected. Why would that be? And if then your company cannot answer those questions, I don't know how long you will keep that customer. And so I don't think we'll get to the bottom, because I think this sort of hype will run out of steam at some point, right? If you cannot deliver at some point, you lose your competitive edge, no matter how sophisticated the algorithms are, or you claim them to be, that you're using. So in that sense, results will take care of this, But in the meantime, a lot of companies, I think, are getting burned by betting on this and hiring a lot of graduates, for example, or people from with a particular background, and it takes a while to sort of rebuild it back to what it was. I think it is fantastic for a company to have a data team. I don't think we live in an age nowadays, and we work and operate in an age where you cannot be without your workers being very data savvy, and you need a data team because so much of our decision making is data driven. Mm-hmm. But you need also domain experts and others to put this all a little bit in perspective, to say, hey, so another thing that I'm seeing, and that is another negative of this hype, is that people sort of think that we have this huge hammer now, which is called the deep neural network or AI, and we can bang any nail with it, right? So sometimes I think that we're seeing baby Bam Bam. So they have this huge hammer and they whack on everything, no matter what the nail looks like. And a lot of people actually out there seem to buy into this. You have this AI algorithm, so you can solve anything. But very often, actually, it's way overkill. And mm-hmm. These deep neural networks, they require two things. They require a lot of data. Not everybody actually has a lot of quality data. They may have a lot of data, and there may be a lot of the richness of that data may not be so high. So then, these AI algorithms are not really going to do all that much for you. Or they don't have the data at all, and they're using these AI algorithms on very relatively small data sets, and then you get this problem of overfitting, and that's not good either. And it requires, of course, a lot of compute power, and so there is a sense now that there are only a few companies in the world that are really competitive when it comes to these very large AI systems. And that's another really interesting part of this. But people, not all companies can actually compete. They just simply do not have the resources. So we're already in a situation where we've really been given, because we believe in these AI systems and we give them a lot of weight, which maybe we shouldn't, that we give power to a small number of companies that have the resources and the data to actually operate those systems. And so sometimes people talk about one of the beautiful things, and I talk about this too, one of the beautiful things about data science is that it is not geographically constrained. You don't have to sit on top of a gold mine. You don't have to sit on top of an oil reservoir to reap the benefits of this new wealth creation, right? The data is the new oil, it's the new gold, and it comes with an enormous amount of wealth creation, and you're not geographically constrained. So there is an unbelievable opportunity, I think, for globalization of this, for countries that are resource poor to really reap the benefits of this, because all they need is data, which flies very quickly from one end of the world to another. You don't have to mine it, right? And it doesn't take years, and you don't have to have the natural resources for it. And they need software, and it's also very easily transferable from one geographical location to another. But we don't really have democratization like this or globalization like this because these types of algorithms, like these AI algorithms, are not available to people because they don't have the compute resources. This new way of decision making, this data-driven decision making, and with the enormous amount of money and therefore power that comes with it, really sits with just a few players. And that concerns me. You've had this in other areas when you talk about fossil fuels, when you talk about gold and minerals, and we've had this monopoly of these very large companies, and now we see again this power concentration and this money concentration in a few of those companies.
At least to some extent, fossil fuels are a resource that people can use without it directly affecting their brains. Whereas, when you talk about like what algorithm is Google running today, and what biases have they worked into it, what decisions have been made that maybe no one in the company is even aware of at this stage. I mean, one person makes a little tweak, 2 months later they leave the company, another person comes in, makes another little tweak on top of that, and you kind of lose track of all this stuff. You've got this is a hugely influential algorithm, whether it's Facebook or Google or any of these companies, that materially affect the way we think about the world, the way we consume information, and how we change our minds about things. I totally agree. I think the centralization, the opacity, these are things that, I don't know, it feels as if we just haven't had time as a species to kind of think about how we would want the world to function in the context where, yes, we want these algorithms.
Yeah, no, it's really interesting to say this. Of course, when you look at where power used to be, so now you say, look, because we constantly use the outcome of these algorithms in our daily lives, because it influences our insurance premiums, it influences so much, right? The news we see, the echo chambers we enter, the movies we watch, decisions are made for us by these algorithms, and we are often not even aware of being manipulated like that. It has a big impact on our lives, and there's power with these companies. But when you look at the past times, when you think, for example, about oil, the old data, right? Oil. We were also heavily influenced by that, because the power didn't sit so much with these companies and these engineers, but it sat with countries, right? So oil, because we were dependent on them, just now we're dependent I wish we weren't as much, but for a lot of our lives, we were dependent on these algorithms. We were dependent on this oil, therefore we were dependent on these countries that had them, and they had the geopolitical power. So through that, they absolutely influenced our lives, to a large extent. You could argue we fought wars because of it. So that definitely impacts us. We've always fought wars on resources. And so whenever you have a concentration of the currency of the time, whether that is data or resources, other types of resources, you will have very large and often negative impacts on people's lives. And so that's not different, I think. But what is different is that more than in the past, maybe, is that now that power sits with companies from a particular subculture. And I'm part of that subculture. That subculture is Silicon Valley, right? And yes, there are other Silicon Valleys around, and they have similar culture. So it sits with the companies with a particular culture, and that I don't think is so good for the world. Now you can say, hey, it wasn't good for the world when OPEC controlled the fossil fuel industry. That was also a particular culture that we didn't like to be dominated by that. But this is one of the reasons, this culture that is dominating our lives so much, that I started with several of my colleagues, this Women in Data Science, because one of the things that the culture has is very strong male dominated, and the culture lives in a bit of a bubble. The same with universities like Stanford or others. We're in a little bit of a bubble. There is diversity, of course, on our campuses, but it is not. It's a diversity amongst the educated, right? A diversity amongst people that have gone through a certain career path, that come from often areas of privilege, and that in Silicon Valley, predominantly male and predominantly white or Asian, right? And a very few URMs. So that is, to me, this concern that I have, is say, wait a second, we are now giving the power of this more and more data-driven decision-making in the world to a particular subculture. And that's not good. I know we want, because to interrogate the systems, to question them, to get a culture in the company that says, hey, wait a second, is what we're doing okay? Are we missing some points of view? Are we looking at this problem a bit too narrowly, perhaps? For those sort of questions to be asked, you need a good diversity of people around the table, and not an echo chamber. So if you are in a company where there's a particular kind of culture, then those questions probably are not going to be asked. Somebody says, hey, is this code robust? Oh yeah, it gives us exactly what we were expecting. Well, that is the expectation in that particular narrow bubble. And so that is what concerns me, about this. Now, so what we have to do is to keep interrogating these systems and questioning these systems, and what you will maybe not surprisingly at all find is that some of the biggest forces in this are actually people that feel marginalized. So some of the most powerful people to question this are Black women, for example. Right? You think about somebody like Tanya Sweeney. at Harvard. She's unbelievable, right? She's like a watchdog on this. You think about somebody like Timnit Gebru, recently from Google and recently fired by Google, and others. There's several up and coming young women like Timnit, like Ridita Bibi, and there's various others. And so they're powerhouses in this, and not a surprise. They come from communities that are really marginalized in this.
Yeah, it's a fascinating problem, isn't it? Because I definitely agree with this idea of like having different points of view represented, and it's so important in this context, especially with technologies that shape our lives like this.
Yeah.
What do you think about the so there's like or diversity in terms of a life experience, and if we talk about ethnicity and gender and that sort of thing. What do you think about as well political diversity? Because of course Silicon Valley is known for traditionally being like, it's like, I don't know, 90% Democrat, something like that. So you have a bubble in a certain sense. Certainly employees at places like Google and Facebook are sort of similar. And this is a dodgy topic, of course. It's sort of like uncomfortable to discuss to some degree. But to the same extent that you have white and male domination in these areas, or Asian as well, and all the stats you describe, it sort of seems like there's the risk of a similar bubble on that side of the equation. I wonder, like, how do you think about like including people from every part of the political spectrum, or like, how do you think about that?
Well, I think it's a great question, and yes, it's very tricky, and I feel on the slippery slippery slope here. You have to really question as a society when any power, in terms of decisions about who gets heard, who gets promoted, and who may not. And by the way, I don't think that platforms have been discriminating against, for example, right-wing leaners. I don't think so. I think that the platforms so far have given access to everybody. In fact, almost too much, right? But what they're in this 1 week before the inauguration of Joe Biden, what of course is going on is say, look, there are some barriers that people overstep, and that's inciting violence. And no matter whether they're from the left or from the right, we're not allowing that to happen. So that's what's going on. I don't think there is a boycotting of people with a certain type of political ideology. You'll find them everywhere. Right? You find them everywhere. But what is the risk for me is what I'm really uncomfortable with is that the potential power, the power sits with just a few people. So do we want Mark Zuckerberg to be some sort of god of the internet that ultimately he decides what or not or what not will be done? I've been very encouraged recently that employees of these companies are actually stepping up and say, hey, wait a second, CEO or big boss, you cannot just make those decisions without us. You saw this with Twitter, right? That Twitter said, okay, we'll do this action for a bit and then we'll revert, and that the company said, wait a second. So now we're seeing maybe more maybe with unionization, we will see more of that, but we see more of the employees actually stepping up saying, hey, wait a second, we have a lot of power as a company and we don't want just this one person to decide. So that's one thought. But yeah, no, absolutely. Your premise of do we need diversity also in terms of belief system, in terms of political ideology? Of course we do. I do at the same time also really believe that those systems need to obey by the normal rules we have in our society. Mm-hmm. And there are rules that say you cannot incite violence. There are rules that say you cannot spread lies if they endanger people. And the big analogy, of course, there is you cannot shout fire in a movie theater if there is no fire, right? Because you're endangering people. But I do think we have to be extremely careful. And that's why I say the power sits with a few companies in a particular subculture for all sorts of reasons. And the same with religion, the same with cultural backgrounds, education, And I do think that Silicon Valley has a problem in that they're not really understanding what's happening outside of that bubble. That's very clear. And so, and it always comes with this concentration of power.
Mm-hmm.
And no matter what time in our history you looked at this, when there's a concentration of power with a very few, with a small subculture, you'll always have trouble, right? Because they're entrenching themselves then too. That doesn't get better if we leave it on its own, because they have this power, and power creates more power, and wealth creates more wealth. And so there is absolutely not a single signal that this group will get to say, hey, actually what you're doing could be damaging, because what they're seeing is this, they're mightily successful.
Mm-hmm.
So yeah, they're getting more and more successful. Power breeds power, right? So why would they even ever question themselves, right? Because obviously people are buying their products, people are using their products, and they may think, well, the people are giving us this power. So we have to really be extremely careful. So instead of countries now, we have these companies. And, there is also a really interesting thing about this. We talk about cultures here, and we have to realize that in the United States, we have various cultures. And around the world, of course, we have very, very strong difference in culture. And that is not just what political ideology you have or what religious beliefs you have, but of course, it's also simply about things like, well, moral campus. That's different, and if so moral frameworks and philosophy, what is fair, what is ethical, differs, around the world. And this notion that even now in this ethics debate, Silicon Valley or satellite Silicon Valleys can actually decide what it means for an algorithm to be fair is really strange. Because our sense of fairness, our Western sense of fairness, or our Bay Area sense of fairness, may be absolutely not aligned with beliefs elsewhere. You go to Asia, you may have a very different sense of what is fair.
Yeah.
So there's also arrogance in us wanting to impose now with this ethics debate our ethics and the way that we're projecting that or translating that into action in our algorithms to say that's what the world just needs to accept.
Yeah. Yeah. I've always felt, I would hate to have to be a full-time AI ethics researcher, in part because the sense of responsibility, I mean, like having to, it's such a scary level of responsibility to have to think through these kinds of problems in a context where philosophers haven't figured out what fairness means for regular humans, and now we're gonna program it into our AI systems. It seems like a pretty daunting challenge.
Yeah, and it's just not well thought out. It just isn't. And there's fantastic work done also by some of my colleagues on this. Say this very relatively simple. I don't want to. It's hard. It's very hard. But say that you start with ethics with just that question: is this a fair algorithm? So you're using a machine learning algorithm to help an insurance company set premiums. The logical question you have then is this fair? Or you have an algorithm to help predictive policing, which has come into light, right? Or you have an algorithm presenting people with certain amount of information when they ask a particular question. Every single time the question should be, as you're designing this algorithm, is this fair?
Yeah.
Are these premiums set in a fair way? So then you say, okay, fine. We can bake this into an algorithm, right? You can make fairness into an algorithm. But don't forget, baking fairness to an algorithm is not done by having a whole bunch of judges or smart people out there who look at every outcome of the algorithm and deliberate and debate whether or not that's fair. No, of course not. That's coded in, right? So that's translated into some sort of mathematical criterion. So how do you measure fairness? And when you start looking at this, how to measure fairness, then there are so many different ways to do this. And every time you do it, you come up with a different outcome.
Yeah.
So, for example, you could
By
say,
the way, that
yeah,
that reminds me of exactly what you were talking about earlier with the neural network problem. Like, if you want to conclude that a thing is fair, you can just choose to analyze it in a way that makes it look fair, right? I mean, this is it sounds almost related to the issue you were raising earlier.
yeah, and you can maybe another way to say it is you can always come up with a metric of fairness that seems to fit. But what I'm saying is that if you have different metrics for fairness, you get very different outcomes. And in a big debate on this came up in the last years about preventative incarceration, right? Where you're saying, okay, we're not going to let people out on bail. We're going to keep them in because they're too dangerous for society as they're awaiting trial, right? And there's this big hoopla because AI algorithms were used to decide the risk factor of a particular accused, right? So not a criminal. They were, you're innocent until you're proven guilty, but they were accused of a crime, and then the algorithm would say what sort of risk factor is associated with this person. Should we just keep him in jail or should we let him out on bail? What is the risk to society of letting this person out? Because that person may have indeed committed this crime. And so there are these algorithms that try to do that. Now, normally that's done by judges. And of course, judges can also be biased, right? Absolutely. But hey, if we're developing an algorithm, we have to try our best. And so the outcome of the algorithm seemed totally biased, right? But even when you start looking at it, though, how do you measure that, right? Is it because there were, in absolute numbers, many more, for example, Black men who were held without bail than white? Or do you say, relative to the population, there were more Blacks than white? Or and what population do you take that relative to? So these are just three questions about fairness, right? What kind of numbers should you see or should you expect to see if this algorithm is fair?
Yeah.
Right. And there's a big debate about this. What is a good way? So normally when you're looking at fairness, it's always put in some sort of perspective. Something is not fair because you're not getting something, say, that other people do, and there is no real discernible reason apart from bias against you why you shouldn't get the same. Statistically speaking, right? So not talking about one individual, but a group of individuals versus not a group of individuals. But even in that, saying how are we measuring that? What do we take into account? What is a group that is, for example, different in maybe education level, wealth, school, about education level I already mentioned, or health. How much can those factors impact the outcome, and are we then talking about something that's still fair or not? It gets, and I'm modeling things up here too because it's so hard to do that cleanly, right? And so edit this out a little bit. So I don't want to come across as being biased anyway. But the whole notion of translating fairness into something we can measure and something we can compute and something we can test is super difficult. And if you say to people, hey, this is how I do that, somebody will have a problem with that.
Yeah. And perhaps rightly so, I guess, because to the extent that this is something I've talked about on the podcast before, but the idea of Goodhart's law, the moment that you specify a metric for something, it stops being a good metric for the thing you're trying to measure because people will find ways to hack it. And so if we say like, hey, we define this as being fair, there are going to be people who look at it and go, oh, okay, like here's this little workaround that like satisfies your metric, but that perverts the whole system, and like now you get a weird result. So
so ultimately we have to always use human judgment, right? We cannot just rely on those algorithms. And so when people ask me, are you saying that an algorithm can never be useful in that sense? I would never say that to say that, but it should not probably be the one arbiter. It should not be the thing deciding everything without question. And that is where we get in. So just as a judge who makes decisions that maybe later, if you put all the decisions of that particular judge together, you think, there's maybe some bias in the judge. You can then start, talking to this judge. You can interrogate him. You can question him. You can decide, hey, this judge is not really impartial. You can do something about it. In other words, you're scrutinizing decisions made by human beings. In the same way, you should be scrutinizing decisions made by algorithms, and always. So, and what I've seen also among students, and I've seen this as long as I've been working in this field of computational sciences, that a lot of people tend to just blindly trust an algorithm. Somehow it comes out of the computer, it's okay. I used to play this trick on students in my class where I would ask them in a simulation class, for example, or math class, I would give them a code that I said, look, I wrote this code. And I want you to apply it to this particular problem and present the results. But I purposely introduced a bug in this code. And if the students scrutinize the outcome of this program, they should see this. They say, hey, that can't be right, and they should question me. But they don't want to question me because I'm the authority. I'm the, they feel a little bit intimidated. I hope not, but, you always have this, get a code from a professor. Who are you to say, hey, I think there's a bug in your code? So very often nobody would. They would present the results and they were all wrong. And when I then start asking them, can't you not see that cannot be the right answer? The response was mostly, well, you gave us the code, and so we assume it's okay. Or it's a code. Of course it's okay. Or it's a code. I didn't really understand what the code was doing, but therefore I'm just going to assume that it's okay. And that is a problem, right? And you see this over and over and over. So a lot of the things that we're trying to do now also with codes they're so complex that very, very often the person giving the go-ahead or allowing the results to go out don't actually understand, those people don't actually understand what's actually happening in the code. And maybe the people that actually got the results from the code, they don't even understand because the code was outsourced or written by somebody else. And maybe the data came from yet another outsourcing. And so when you look at something like a Boeing 737 MAX, and you look at what happened there, that's exactly one of the problems, right? That people say, okay, this is fine, didn't really understand what's going on. So in complex systems, you always have that. But we have to get to a place where we're always really aggressively scrutinizing outcome of codes and questioning these outcomes and have this dialogue and be patient with results. So maybe the thing here is that if you're wondering whether or not something is fair, change your metric for fairness and see what comes out then.
Yeah.
Listen to the people that say they're being disadvantaged and think about, hey, what was it in the code that made me that? Maybe my translation of what I considered fairness is wrong or incomplete. And the way around all of this, I think, is to never just rely on one code or probably one person to make these sort of decisions. So in the penal system, the AI codes could be useful to complement the judge's opinion. So I could see judges saying, hey, what would the AI code have given? And then sort of question their own thoughts and use it as a check. I think that could be useful, but not just blindly trusting. So it's, we are in an era now, I think, where our lives may not be so complex, but the systems we're relying on in our lives are extremely complex, and we're going to be running into these things and these unintended consequences of what we're relying on and what we're building. And the best we can do is always question and to really be wary when power starts sitting with just a subculture or a couple of individuals.
Well, I think that's a great note to wrap things up on, a beautiful tie together. Thanks so much. Actually, Margot, before you go, I do want to give you the chance to plug women in data science, because I think it's an important thing to get out there. Would you mind sharing any details on your, I guess, your upcoming,
Absolutely. So we started WIDS, as we call it, Women in Data Science, WIDS, in 2015, really as a way, as a platform to promote outstanding work done by outstanding women, to inspire everybody really in the field, regardless of gender, and to educate and to support women also in the field, and really everyone. We're very inclusive. And the reason why we started this is because so many conferences up to then and still now were mostly promoting work done by men. And that's, because many of the people working in the industry of data science are now a very small percentage of women, but also because the work of women was just not really promoted. So if you looked at, okay, there's 15% women or 15% of conference keynotes or conference awards or journal publications created by women, no. So we were, it was disproportionate. So I thought, hey, let's, because I know so many women doing amazing work in this field and they are always in the background. So let's bring this up. So we started this with just a normal conference on Stanford campus, and we started live streaming that, and we got a surprisingly large number of people.
It's a huge movement now. I mean,
we built it out and we made it worldwide, and now 5 years later we're in over 70 countries, and we have over 200 events around the world, and over 100,000 people connecting with us every year. So WITS is an organization with lots of different things. We have a podcast that I host. We have a datathon that is out there right now, where teams from all over the world can contribute to solving a particular problem. This year, it's a medical problem related with ERs and diabetes. And then we have educational outreach, and we have meetings where people come together and listen to these amazing women. And we always have a central conference. This year it will be a 24-hour virtual event where we go around the world in those 24 hours featuring speakers from different regions. And that's on International Women's Day.
Are you going to be awake during the full 24 hours?
Yes, period? I'm going to be the mistress of ceremony.
My goodness.
For the 24 hours. And I'm sure the adrenaline and the excitement will just keep me going. But we'll have talks, we have panels, we have breakouts. We have an educational channel that runs along it as well, where we offer workshops. Again, all these workshops are taught by women for everybody. And so that's going to be very excited. And you can find all that information at widsconference.org, widsconference.org.
All right, so we'll include the link as well in the podcast that'll the blog post that'll accompany the podcast. Margot, thanks so much for joining me. Really appreciate it. Had a great time.
Yeah, thank you so much. It was a wonderful discussion.